Welcome to the ArcTech AI Institute. Today, we delve into autoencoders, foundational neural networks for unsupervised learning. A well-trained AE yields a latent space that captures meaningful semantic features, making it useful for dimensionality reduction. While effective for compression, standard AEs aren't inherently generative. Their latent space might not be continuous or smooth. This brings us to Variational Autoencoders, or VAEs, which address the generative limitations of standard AEs. VAEs take a probabilistic approach. Instead of encoding to a single point, the encoder outputs parameters of a probability distribution. From this distribution, typically a Gaussian, a latent vector z is sampled. This makes the latent space inherently probabilistic. To enable backpropagation through this sampling process, VAEs use the reparameterization trick. This trick separates the random sampling from the network's trainable parameters, allowing gradients to flow during training. The VAE loss function has two crucial components, the reconstruction loss and the KL divergence loss. Similar to AEs, the reconstruction loss measures how accurately the decoder rebuilds the original input from the latent sample. The KL divergence loss regularizes the latent space, forcing the learned distributions to be close to a prior, usually a standard Gaussian. At their core, autoencoders aim to learn efficient, low-dimensional representations of input data without explicit labels. This regularization ensures the latent space is smooth and continuous, preventing gaps and facilitating meaningful interpolation. The probabilistic nature and regularized latent space empower VAEs for powerful generative modeling. By sampling random points from the prior Gaussian distribution and feeding them to the decoder, we generate entirely new, plausible data. Beyond generation, AEs and VAs are used for anomaly detection, dimensionality reduction, and disentangled representation learning. Autoencoders provide powerful representation learning, while variational autoencoders extend this for robust generative capabilities. Join us next time as we explore more advanced generative models building upon these foundational concepts. Autoencoders consist of two main parts: an encoder that maps input to a latent space, and a decoder that reconstructs the input. The encoder's primary function is to compress the high-dimensional input data into a dense, lower-dimensional latent representation. This compressed representation, the latent space, captures the most salient features of the input data. Conversely, the decoder takes this latent representation and reconstructs the original input data as closely as possible. The core of AE training is minimizing reconstruction loss, the discrepancy between the original input and its decoded output. For continuous data, mean squared error, MSE, is common. For binary or image data, binary cross-entropy is often preferred. The autoencoder is trained end-to-end using backpropagation to adjust weights, minimizing this reconstruction loss.